Okay, so the next example, this example is going to evaluate how do you understand drag on a body? So drag is the force opposing the free stream or the force on a body that's in the direction of the free stream. Um, so what is the drag on a body, and determine it using a wake profile. So imagine, so this body shown in red is being exposed to a free stream velocity with a density of rho as a free stream pressure of P infinity, and the flow moves over it and it leaves this wake profile. So you measure the velocity in the wake. At some point, it approaches the free stream velocity, but it has a deficit that corresponds to the drag, and then it rises back to P infinity. What we're going to do is say that this wake is based on the center line of the body. It is observed from C on 4. The reality of the scenario is that this kind of step profile is not normally observed, but it makes it nice for analysis methods. So what do we want to do? How do we tackle this problem? First thing we do is we make our assumptions. For this case, we're going to assume rho is constant. Steady flow. Things aren't moving, these sorts of things. P approaches P infinity at far field. And we're also going to make the assumption that no shear forces far field. Why are these two important? Because remember, in momentum theorem, you form your control volume and then you have to evaluate pressure and shear forces as well. And we don't want to evaluate them way out here and way out here. Okay, so in the context of this, the next thing we want to do is formulate our control volume. And I'm going to formulate the control volume to start here. And it's going to start here. We have a little bit more complicated character on the sides. So we have an inlet on surface 1, this complex region on surface 2, an outlet on surface 3, and don't forget surface 4, which gives us the ability to assess forces on the body. Okay, so a few comments here. One, why is this defined, okay, let's go through a few comments. One, our ds, when we start evaluating our integrals, is always outward normal. So out of the control volume. 2, we put this here because anywhere above here, so in the context of our momentum equation, which basically says dt rho v d v plus rho v v dot ds equals negative pressure plus. So what we're going to do is use this term on surface 4 to give us our drag, or the forces. This term on surfaces 3, 2, and 1 are going to go to 0 based on assumptions 3 and 4. This term is going to be the momentum flux out. If we're above this point, that momentum flux is going to be equivalent. Hence, we don't need to evaluate it. So it enables us to focus on this point and this point. We have one issue though. I don't think I described. So this is where we're coming from. So the key thing about surface 2, which are these two surfaces right here, is that they are streamlines. They don't always have to be streamlines. We want them to be streamlines. And the reason why we want them to be streamlines is we don't want to have flux. If they're not a streamline, flux can come in. Flux will go out and in as the flow moves around this body. We don't want to evaluate that. We want to just say, we don't even have to assume they're streamlines. We just say these are streamlines. And the only place where it makes sense is at the end point. This follows the streamline there, and the beginning point. And the beginning point demands understanding what is this y value. We're going to call it H1. How do we close that out? We use conservation of mass. So yields H1, or starting point of streamline. Okay, so this is where we're going. So just to recap, we're using, what we need to do is find the forces via this of the momentum equation to obtain our force. This term's gonna go to 0 because it's steady, and we're gonna evaluate momentum flux out of the system. So the momentum flux out here minus momentum flux in here. Okay, so how do we do this? First step is conservation of mass. What does it say? That the change of mass in the system is equivalent to momentum flux out of the system. We're looking at a steady flow. That term goes to 0. And what we want to do is break this term up into 4 different terms, one on each control surface. Okay, so the first thing we want to do is evaluate this first control surface. So we have, so a few things to note. We have a constant velocity times an area. We have this dot product term. So so if we take this to the side, V dot ds is going to equal, so V is this way, V1 is I S negative I ds. We take that dot product, this dot product, we're going to end up with negative V infinity ds. So when we look at that, come back to our equation. What we could do is bring this back down. Density is a constant. We evaluated this as this, which is a infinity, a negative sign, and an integral of ds. What is this double integral of ds equal to? This overall integral. Just one more note. L, we're going to say that this is all has an into page length L. That's probably not a good. So L is thickness into page. So 2H1 times L is our area. So this is our integral 1. So for integral 2, I'm going to put this in another color to keep it a little bit different. For this integral, we have v dot ds. So remember, this is on this. So our velocity is always tangent to that streamline. So this is the requirement. So our v2 dot ds 2 is always going to equal 0. So the third one, this is the outlet. So our velocity is to the right and our ds is to the right. So v3 ds3 is going to be the infinity on 2 times I. Yes, 3 equals I ds. So this is always going to be e infinity on 2 positive sign times ds. When we do this, perform this integral, we could pull out rho. We could pull out v infinity on 2. It's a constant, and we end up with yes. This integral equals 2 times c on 4 times L. So remember, the height of this is c on 4. We have 2 of them, and we multiply them times L. Just to comment here, if this velocity is not constant, we have to keep it in that integral, which is more consistent with a typical wake. So this was surface 2, this is surface 3, and we go to surface 4. Let's look at surface 4. Surface 4, we cannot have flow penetrating the body, so we have flow tangent to this ds, hence, again, it's normal. So in that condition, v4 ds4 is always going to equal 0. So we have another 0. So if we pull all this together, we have an equation that says rho v infinity times 2h1L plus these two are going to cancel out. So rho v infinity c on 4L equals 0. So all we need to do is solve for h1. H1 equals So these cancel out. So our H1 is going to equal, L also cancels out. And it comes to a pretty clean answer where we get that H1 equals C 8. So what that tells us is that this streamline can only be connected between this point and this point if H1 is C on 8. So it makes sense, right? You conserve mass. If you have twice the velocity coming in on this side than on this side, its H1 value becomes half as it is going to be on that. Okay, so this is key, right? We now have defined how this streamline can be connected between our inlet surface at 1 and our outlet surface at 3. Now we have enough to move forward and go to the conservation of momentum. What does this do? Yields drag. Conservation of momentum is written as time rate of change of momentum inside the volume plus the momentum flux rho times V. That's the momentum times the flux out of the control volume, which is going to equal pressure integral of the integral of pressure around the body minus the shear forces of the fluid on the outside of the control volume. Okay, so this one, similar to before, is going to be 0 because it's steady. This one we have to evaluate on each surface. Let's evaluate this in 2 different times. We're going to first look at the left-hand side of the equation and then move to the right-hand side. Let's start with the left-hand side. And what we're going to do is break this integral up into 4 different integrals again. So we have momentum flux on surface 1 plus momentum flux surface 2 plus momentum flux on surface 3 plus the momentum surface flux going outside of surface 4. Okay, the momentum flux going out of surface 1, similar to before, this is identical to what we saw. This is going to be V infinity, negative V infinity ds. So this term ends up being constant rho V infinity times I, which is this term, V infinity integral of ds. Again, this is going to be H1L or CL on 8. The second term, remember the second term is the streamline, where that term equals 0. So that's going to equal 0. The third term, recall this equals positive V infinity on 2 ds. This term is going to be V infinity on 2 times I. We plug all those in, we get rho V infinity on 2 times I V. It's not a, this is a positive times V infinity on 2 the integral of ds. This one's going to be C on 4 times L. This one, that equals 0 again. Because this is the momentum flux through surface 4, and we cannot have velocity through it, so there's 0 flux. So our left-hand side becomes, if we had to pull this all together, rho times V infinity squared. This side's going to be negative. Times C times L on 8. This one's going to be positive. Rho V infinity squared on 4. Forgot the, you can't forget these directions. So rho V infinity squared on 4 times CL on 4 in the I direction, which can be rewritten as rho V infinity squared on 8 times CL So this is 1 and 16 to minus 16. So that's a momentum flux lost. Does that make sense? Or I mean, if that doesn't make sense, it's basically we're doing 16 minus 2/16, giving us that term. So this is what our left-hand side equals. Now we want to go to our right-hand side, which is this term. Very similar to before. We want to do, so right-hand side, we want to do our pressure. I'm going to just do it on surfaces 1 through 3. Negative ds minus surface 4 pressure times ds plus 1 through 3 shear force on the fluid plus surface 4, we have a shear force on the fluid. So remember in our assumptions, we said that these two things, in the far field, these aren't acting. Essentially, all these boundaries are so far that the pressure has have become back in equilibrium with pressure, and that we do not have shear forces acting on it. So when we do that, this term, okay, without shear forces, this term goes to 0. Without pressure forces, if all of them are P infinity, it actually becomes 0. You could evaluate pressure on every single term, but they're always equal and opposite. It comes back to hydrostatics. And if you have an equal force on any arbitrary shaped body, it will become, you have an equal pressure force on an arbitrary shaped body, it'll be 0. What does not go away are the pressure and shear forces on surface 4. What are those? That is our body of interest. So what this gives us is a force of the body on the fluid equals negative pressure on 4 plus the wall shear. No, the shear on the fluid, that is going to equal negative drag, which is what we're after. So let's compute this. How do we compute it? We plug it back into our equation. Remember, we have our left-hand side and our right-hand side. Our left-hand side was given as this equation right here, negative rho v infinity squared chord times L on 16 in the I direction, which is going to be equal to our right-hand side, which is force of our body on our fluid. We don't even have to compute these. We already know that they're the force on the body. Why do we know it's our force on the body? Because the forces that the body is exposed to are the integrals of pressure and wall shear. Okay, so this is basically it. What does this tell us? It tells us that the force that the body pushes on the fluid is given by this, or the drag equals the opposite, negative FBF, which equals to positive rho v infinity squared times the chord on times length on 16. So this is one way to obtain forces on a body by evaluating pressure weights.